hashing, what we always do when we talk about a machine learning paradigm, we start with asking what the representation is, what the representational power is, which implies what the hard bias might be. And then the second question we ask is, how do we find, within the representation power, how do we find hypotheses that are consistent with the training data? And there's a search issue there, and there's also a preference bias or soft bias there. Assuming there are many hypotheses that are consistent with the data, which ones are we going to land on first? Either as a result of the way we do our search, or as a result of an explicit preference for some things over others. Okay? We dealt with these questions in the context of decision trees, and we're now dealing with them in the context of neural networks. What's common to neural networks is that they have many inputs, possibly many inputs, possibly many outputs, although often we will deal with a simple case of just a single output. Let's put many outputs there. The inputs could be real values. They could represent some measurements in the environment. They could be positive or negative or anything in between, some real values. For some problems, they could be Boolean. Just Boolean would be represented by two different values, and you have some discretion if you want to use 1 and 0, or +1 and -1, or any other set of two values. It turns out that mathematically there is not much difference. In fact, any function of Boolean variables that you can compute with a neural network with, say, the value 0 and 1 as inputs, you could also compute it if the inputs were some other two values, 3 and -5, or any other two values. You would need to change the weights, but in principle there's no difference. So the representation power does not change if Boolean inputs or binary inputs are represented by these two numbers or some other two numbers. Representation power is the same. Same is probably true for the output within limits as we'll discuss in a minute. So generally you have inputs that are binary or continuous. I should say binary, categorical or continuous, because they could be non-binary. They could have 3 possible values or 5 possible values, or they can be continuous, which is the most common case. And then they're connected through some number of intermediate units, which may not have to be arranged in a layer. It could be any kind of topology, but the common to all these topologies is that it's a DAG, directed acyclic graph. Namely, every connection has a direction, and there are no cycles. In fact, you could have cycles. These are called recurrent neural networks, and we'll just mention them briefly. But the most common case, they're non-recurrent, and therefore you have a DAG, and somehow it's connected at the end to the outputs. The computing components of this are these individual neurons that are inspired by real neurons in the brain. They have multiple inputs and possibly multiple outputs. And the way they work is in 2 stages. All the inputs are summed together using a weighted sum, weighted by the weights here. So if this is unit I, the net going into unit I is defined as I can write it in multiple ways, W0 times 1 plus W1 times X1 plus Wn times Xn. Also can be written simply as the weight vector dot product with the input vector. If the input vector is understood to be prepended with x bar is 1, x1, x2 through xn. So remember, by convention we have an x0 which is set to 1, which is a way of dealing with this component. This component goes by many names. It could be called a bias, somewhat different than the bias we talk about in machine learning. It's a bias of that unit. It could be called the negative of the threshold of the unit, because now we're going to look at this and ask if it's greater than or lower than 0, Whereas before, without this, we would look at this and ask if it's greater than or lower than negative W0. That's the same question. It can be called bias, it could be called threshold or negative threshold, or if you're an EE major, you can call it the DC component. The sort of stress component does not depend on anything else. So this is a net. And then the output that comes out of the unit is some kind of function of the net that comes into the unit, where this function is called the transfer function. Everything about neural networks that I said so far applies regardless of the transfer function, but the interesting thing happens in the transfer function. If you choose different transfer functions, you end up with different representational power, different biases, different issues with search. So the first transfer function we dealt with was, what was the first transfer function we dealt with? The only one we had time to talk about. Please? Step function. We mentioned the step function. I don't think if we dealt with it. I don't think we talked about the representation power. I did mention the step function. I did draw it for you, but there was another function even simpler than the step function. What's the simplest function there is? Yeah, a line identity function. The function that produces the output, the input as the output. So that is the identity function, and we call such units, such neurons, linear units. So number one would be linear units that are defined as sigma of net, well, I don't know what to call it, sigma of, I don't want to call it x, sigma of z equals z. Just the identity function, or in a drawing, it would look like this. This is the identity function. It's a 45-degree line, goes through the origin. So it's a transfer function that doesn't do anything. Basically, it just passes through the input. Once you decide on the transfer function, now the class of functions that are implemented by neural networks is well defined. As you vary the weights, you're implementing somewhat different functions. And then the question I ask you is, what kind of functions can be represented by a linear unit, a single linear unit? And your answer was linear functions, which is a way of rehashing what we already know. But we all have a sense of what linear functions are. If you think about it geometrically, it's a linear function defines a hyperplane through space. And then there is a perpendicular direction to the hyperplane. And the linear function basically measures your distance from that hyperplane along the perpendicular. So it's easier to see in a two-dimensional, well, even two-dimensional is hard to see. Imagine x and y, the two-dimensional space is the floor in this room, and a hyperplane would be a line going through it, and then a linear function measures your distance from that line. In 3D, imagine this room is your space, 3D space, and a hyperplane would be some two-dimensional plane going in some angle through this room, and what the linear function calculates is your distance from any point in the room, the shortest distance to that plane. Harder to visualize in higher dimensions, but the principle is very similar. If you have a 10th dimensional Euclidean space, x goes from 0 to 10, remember 0 is just the bias, any set of weights will correspond to a 9-dimensional hyperplane through this 10th dimensional space. And then any point in that space will be assigned a value based on its shortest distance to that hyperplane. So that's the geometric way of thinking of a linear function. The algebraic way of thinking of a linear function is here. It's an inner product between the point you're at. Well, I'm talking geometry again. It's an inner product between two vectors. The input vector and some weight vector. The arithmetic way of thinking about it is it's a weighted sum of the coordinates. So many different ways of thinking of the same thing. Now I pose the question, so this answered the representational question, the first question, with regard to a single linear unit. And now I ask you, what about the second question of searching the space for a particular member of this class, a particular set of weights that match your training data? Perfectly, if possible, or as close to it as if not possible. Remember I asked that question, and I got an answer here from the first row, but he's not in the first row. He's in the first row. I got an answer here. Remind me of your name? Dan. From Dan, that there's an algebraic way of solving it by writing it down as a set of linear constraints. So the input would be x11, x12 through x1n, and they would have a certain output, desired output y1, and then there would be x21, x22 through x2n with the desired output yn, y2, and then it goes all the way to xm1 through xmn, the desired output ym. And if you took linear algebra, you can put, I'll move this to here, y1 through ym, and put this here, and put my unknowns here, and put a equality here. Do you recognize this as a matrix times an unknown equals some other vector? And what are my unknowns? The weights, the w's. In fact, it starts from w0 and goes through wn, and for it to start from w0, I have to start here from x10. But x10 is always 1, so it would be 1, 1, 1. So this would be my matrix, and it's about an n by m problem, and I can invert the matrix, and if it has an inverse, I have my solution. If it doesn't have an inverse, linear algebra gives us a way of finding the least mean squared error solution. It also involves inverting matrices and transposing matrices, and we're not going to get into that. Just to note that linear algebra can solve this, but it's not a trivial solution. How much time does it take to invert a matrix? Does anybody know? Let's say a square matrix n by n. Yeah, so the simplest solution is n cubed. You know, if you do a high school solution, you do Gauss elimination or any one of these techniques, is n cubed. But there's been tremendous amount of work on doing it in less time, and I don't know what the latest result, but it's somewhere between square and cube. It's n to the power of 2.7 something. And of course, if some matrices are sparse, there are ways of taking advantage of that, making it even less. It's polynomial, but it's not a trivial polynomial. You know, when n is 1,000, it takes time. But it can be done. And then I said there's another way of doing it, not algebraically, but more computationally. And we talked about gradient descent. And to do that, we defined our error function. What is our error function a function of? Given a topology and giving a set of training examples, x's and y's, the error is a function of what? It's a function. It's called an error function, so it's a function of some arguments. What are the arguments? The weights. It's a function of the weights. Different weights, different value of the function. And it's defined as, we like to put a half here, it's not crucial, sum over the training examples. I apologize if I change indices on you. I don't know if J was used for training examples before or not, but of the error of each individual item. And the error of each individual item is what the real value should have been, which is yj minus what the actual output of the network is for this fixed set of weights, which is w dot x. W is fixed, x is indexed with j. And then we square this. Squared error. We defined our error to be squared error. We don't have to. We can define our error in some other way that makes sense, such that when this equals this, the total error is 0. So we could make it cube or fourth, whatever. We want it to be always a positive component. We talked about that. But we can also use a log version. And in fact, there are times when you use a log. An error function involves a log. And I'll tell you when that's appropriate. But the most common error measure used is a squared error measure, also known as mean squared error. Now, I said there are many reasons for that. One is that it's the appropriate measure if the process you're modeling has a Gaussian error attached to it. Second is that it's really easy to take the derivative and you end up with a linear component of the derivative. There may have been another one. Okay, but this is our error function. And now we can actually draw the error surface, which is the last thing I did last time. Here's the error surface for the case of a one-dimensional input. Because it's one-dimensional, there's x0 and x1, which creates a two-dimensional error input space. I'm sorry, weight space, two-dimensional weight space. And then the third dimension is used to draw the magnitude of the error. Error, by definition, is never negative, so it's always above the surface, or it can touch it. In this case, the error surface looks convex. Specifically, the shape of the function is concave. The surface is convex. I don't know if you're familiar with these topological terms. A function can be convex or concave. Generally speaking, convex is like this, and concave is like that. So concave is U-shaped, and convex is upside-down U-shaped. A surface or a shape or a volume or a set can be convex, meaning that every point on it can be seen from any other point in the line that goes right straight through that set. So I'm not giving you a complete detailed definition, but just an intuition. This is convex. This is convex. This is not convex because there's a point inside here and a point inside here that the straight line takes them outside the shape. So sets can be convex or not. Functions can be convex or concave. Typically, when you have a convex or concave function, the area that's bound between that function and, let's say, the zero line is convex. So this is what we have here. The area above the part of space that's above the function is a convex set. What's important to us is the function is concave, which means it has a single minimum. That would come in handy. We talked about what we can do with gradient descent. A way of reaching a good solution is by starting at some random point in weight space, namely choosing some random weights, and then calculating the gradient of the error function at that point and taking a small step in the direction of that gradient. And then stopping, calculating the gradient again, and taking a small step in the direction of that gradient. This is the essence of gradient descent. Okay? I gave you the example of standing in the desert in a very dark area, which means you cannot see what's happening outside your immediate neighborhood, and you can just feel the ground with your feet to see which direction is the steepest descent. This is what a gradient does. Gradient is a vector function of a scalar function. So the scalar function here is the error function. It's a scalar, meaning it's a numerical function that assigns a single number to each place in the Cartesian space. And the gradient is a vector function of it, namely it assigns a vector, a direction for each point based on which direction is the steepest change and also the magnitude of that change. So if you follow this process of making small steps along the gradient, you'll end up where? In the local minimum. So this is not a, fail-safe, guaranteed best thing to do, but it's a reasonable thing to try. In the case of this example, because the error function is convex, rather concave, but we often say, loosely we say convex, there is only a single minimum, and therefore finding a local minimum means finding the global minimum. There's just one minimum. So no matter where you start, if you take small steps along the gradient, you'll end up at the minimum point. I can tell you that in the case of a single linear unit, that is indeed the case. And we can actually prove it algebraically, that the error function is concave and therefore there's a single global minimum and you will always find it. We can use gradient descent in other cases where that's not true, where there can be many local minima and therefore you may not find the right one. Usually, to actually implement gradient descent, you need to find the form of the gradient, and that's done by taking a derivative of the error function. The derivative of the error function would be, here's the error function, would depend on the form of the error function. Assuming the error function is quadratic, it will depend mostly on the form of the transfer function. So we will use the chain rule of taking the derivative to take the derivative of the square thing, but eventually we'll have to take the derivative of this part. And this part in the general case is not just w times x, but it's sigma of w times x. Right, so we'll have to take a derivative of whatever sigma is. Just keep that in mind. In the case of linear units, it's transparent because sigma is just a unity function. Okay, so here is the algebraic notation I'd like you to be familiar with. A gradient, which is written as this upside down triangle, so this is a gradient of the error function, the function of the weights, and since a gradient is a vector function, here are its components. The components are the partial derivative of the error with regard to each one of the weights, starting from W0 going to Wn. So basically we will need to take the derivative of the error function with regard to each one of the weights, calculate what it's equal to, apply it to a specific value of the weight, and then take a small step in that direction. How do we come up with this rule for changing the weights? For this I want to show you an actual example of working out the gradient descent rule. So here is some algebra or calculus for working out the value of the partial derivative of the error with regard to a given weight for the case of a linear unit. So let's follow it through. This is the derivative with regard to any one given weight of the error function, which is defined this way. Just to equate the notation, T sub D is, T stands for target or teaching signal. This is the correct value. This is what I call the Y here. And O is the output of the neuron. the sub d is for dimension. So we called it here, what did we call it here? I think we called it I think it's the index over your input space. We take the half out of the derivative, we take the summation out of the derivative, so we apply the derivative with regard to each. I'm sorry, D is, should have corrected me, D is data, for data, for how many training examples. This is our index J going from 1 to m. How many training examples? The error function is defined as a sum over all your training examples, over the error of all your training examples. So now we're moving the partial derivative sign into each one of these alone. And of course, applying it to a quadratic term gives you 2 times the derivative of this. So 2 comes here, which of course will cancel with the half. So it's 2 times this to the power of 1, which is here, times the derivative of this, which is here. The 2 and a half cancel. We're left with this thing here. And now applying the derivative of this to this thing, t is what we called y, is a constant. It is not affected with regard to the change of the weights. Changing the weights does not change it. So the partial derivative of the constant with regard to the weight is 0. Now we expand our output of the neuron for training example D as an inner product between the weight vector and the input for example D. This is where we would have had the transfer function. But luckily we don't. It's a simple transfer function. The derivative of this with regard to component Wi is simply that component that multiplies Wi, which is negative x id. So we're left with the partial derivative of the error with regard to some given weight Wi is a sum over all the training examples of this amount, which is the error in that training example, times the negative of the value of the relevant input for this training example. How do we interpret this? If you have a training example that set of weights does beautifully with, that set of weights solves exactly, then this would be 0. And therefore, this weight will not need to change. If it doesn't do beautifully, if it overshoots or undershoots, this gives you both the magnitude of the error and the sign of the error. Did our current set of weights overshoot for this training example or undershoot? What you have here is a dependence on the particular input number I. So imagine an input number I was 0. So even though our current network overshot or undershot, we don't need to change the weight if this is 0. So how much we change the weight depends on how active this input is for this example. And of course this is averaged over all of our training examples. So now we can go back to the training rule. You summarize the gradient training rule by saying that the delta is a change. The change in the weights in the current iteration is proportional to the gradient of the error. It's negative proportionality because we're trying to go towards lower error. And this eta thing is called the step size. It's just a small number that tells you to make a step in the direction of a gradient, but a small step. Now, how small should this number be? The answer is we don't know. There's no theoretical way of choosing it. There are 2 considerations. One is if you make it very small, you will need to repeat the gradient descent step many times, thousands of times, millions of times, if you make it too small. If you make it too large, you're running the risk that you're overshooting in the direction you're going, and it's especially important if the error surface is not as nice and smooth as in our example, but full of bumps. You remember that you're making your decision on the local slope, in fact on the infinitesimally local slope. And if the local slope does not really reflect the conditions a little bit further away, then you'll be going in the wrong direction. So an example of that would be, you're here, let's say you're here, you estimate the local slope as being in this direction, So you should go in this direction, but if you go too far, you'll end up going to here, overshooting the minimum. If you're careful and you take small steps, you'll go in here and here and here, and you end up getting to the bottom. This is a bit oversimplified, but this is what pushes you in the direction of not taking step size that's too large. How do you choose a step size? I don't know. I mean, there are all sorts of rules of thumb. There are all sorts of rules that you choose something, then you see what happens, and you make dynamic adjustments based on whether you made a big change or not. There are rules that look at the second derivative that measures the curvature of the error, and if the second derivative implies a strong curvature, then you slow down your step size, make it smaller, otherwise you make it larger. There are a variety of other heuristic techniques for dealing with that. Okay, so this is a little detour. Let's go back to our main story. We're interested in representation, we're interested in search and bias and learning. Apply all of this to a single linear unit. Representation power is linear function. Search, we seem to have a good solution. Either do the algebraic solving of a matrix or do gradient descent, and you're guaranteed to find the local minimum. These two questions of representation and search always go together, in a sense that the larger your representation power, the harder the search is. Well, maybe that's not completely right. The other way is right. If your representation power is limited, is it always hard to find? No, forget that. No. Let me make a different connection. Connection between the representation power and learnability. Can I make a generalization there? I'm not even sure I can do that. So let me just say that in this specific case, learning is a breeze. This gradient descent procedure that we described is very easy to do. Algebraic inversion is easy to do. But you can only represent linear functions, which is not very satisfying, because most interesting things that we want to model are not linear. In fact, if we knew they were linear, we didn't need machine learning. Statistics, mathematics are full of ways of modeling linear processes. It becomes interesting for us as machine learning people when it's highly nonlinear, and we're still trying to learn from examples. So one natural way of trying to expand our representation power is, instead of using a single neuron, we will use a network of neurons, of linear units. So what would be the representation power of a network of linear units? Did I ask you that already? So now you are allowed to put together as many neurons as you want, in any topology as you want. Each one of them has a transfer function that's just linear. And you're allowed to vary the weights as much as you want to represent whatever functions you can represent. And the question is, what did you gain by doing that? What kind of functions can you represent now? Can you represent any function?
Still linear function.
Still linear function. Why?
Linear combination of linear functions is still linear.
A linear combination of linear functions is still linear. Is that true? Do you buy that?
Approximate with linear functions. I mean, you can approximate a curve by just adding together a bunch of linear functions.
Piecewise linear, right? What you're saying. So let me first resolve the tension. Yes, you're correct. A linear combination of linear functions is still linear, and therefore a network of any size, of any topology, that implements only linear transfer functions can only represent globally linear functions. But you're right too that linear functions can be used piecewise to implement or to approximate any functions. If you have this complex function, you can say from here to here I'm going to approximate with this linear functions. From here to here I'll use this one, and from here to here I'll use this one, from here to here I'll use this one, and so forth. You can follow this entire. But you will need a mechanism for deciding based on the input which linear piece you're going to use there. And that decision is a nonlinear decision, and our neurons are not able of doing that. But if you can add little switches in there that say go this way or go that way, use this computation, this computation, and you're right. You can use linear, what's called piecemeal linear approximation. So, to summarize where we are, we wrote number 1 there. Linear unit is linear function. And learning is good. We can learn it easily. Our number 2 attempt is network of linear units. And our disappointing conclusion is that it didn't increase our representation power. It is still linear functions. And we don't even care about learning, because if it didn't give us any more, we might as well stick with a single neuron. Let's ponder for a moment what this equivalence means. It means that if you have a fancy network of 100 or 100,000 neurons that are all linear, that are connected with hundreds of thousands or millions of weights, and they map some n-dimensional input to, say, a single output. No matter what weights you assign, there exists an equivalent network of a single neuron with just one set of weights going into this neuron that implements the exact same function. So it's a many-to-one mapping of many sets of weights, many topologies go into a single neuron that does the same job. Question?
Would you be able to find the weights in a correct manner, such that you will be able to train that many weights so that you will get the equivalence? I mean, that assumes if you chose a really big network to approximate really the single neuron, you might make mistakes in finding your weights.
You're talking about the process of taking a single known neuron with known weights and then finding a large network that implements the same thing. You're saying, is that easy or hard?
I'm saying you might not be able to determine the weights correctly.
From training data? So you can train a network of linear units using gradient descent in pretty much a similar way. It'll be a lot more computation, and there would be many answers, not just one. I don't think it will be hard, but it will be more computation. That's for sure. I thought you were asking about the opposite direction. You're given a large network of linear units that does something, and you say, find a single unit that does the same thing. How hard is that? Now you're asked to train or to learn a function with a single neuron, not from examples, because any set of examples would be finite. You're asked to do it from an existing large network. Can you think of a way of doing that?
Collapse nodes together.
Collapse nodes together?
If they've got the same sets of inputs, you can just sum their weights, because, or whether, depending on what they are, then connected to the output. But
yeah, so you can do something like that. You can solve it algebraically, actually, very straightforwardly. Here's the output. Here are various inputs. Some combination of layers and non-layers. The output would be a linear sum of the inputs that come into it, call it Z, whereas Wi is Zi, whereas the Zi's themselves are a linear sum of some other weights. I don't know what to call those. There's some different kind of W. This is WA, this will be WB, so this is A, B, C, D. With some other, I don't know what to call Z's, call them U's. I don't want to get too tied down in notation, but the idea is that you can take these inputs that come into this final linear integrator and expand them. Instead of writing it this way, write it as a sum of weights. And then you can take this one and expand it. And you can keep working your way down to the original inputs. So in the end, you will be expressing the output as a fancy combination of summation and multiplication of weights of the intermediate units. And then you just arithmetically compute what these values are, and you end up with the weights that you needed. So this may not be a bad exercise to do with a two network unit. Okay, so one linear unit is easy but not very exciting. A network of linear units is equally unexciting, and therefore we don't care if it's easy or not. Our next step is to introduce nonlinearity. So our nonlinearity would be the step function. So our number 3 here would be sigma of, did I call it net, will be, say 1 if and only if net is greater or equal 0 and 0 otherwise. And in a picture, it would be this step function. There's some arbitrary choices here. I didn't have to choose 1 and 0. I could choose any two values. In fact, the common choice is -1 and +1, in which case the purple would have started here. Second thing, I didn't have to choose my threshold at 0. But I chose it at 0 because I already have the degree of freedom in my threshold, also known as W0, or negative W0. So I can adjust that W0 and always say that my transfer function transfers it, steps at 0. Because saying W times X is greater or equal 0 when X goes from 0 to N is the same as saying, and W goes from 0 to N, it's the same as saying does W times X greater or equal negative W0 when W goes from 1 to N and X goes from 1 to N. So by putting the notation of X0 always equals 1 and W0 being the negative of the threshold, I'm allowing myself to choose 0 here without loss of generality. This kind of neuron is called a perceptron. And it actually has been studied in the 60s intensively by two different groups of people. One, it was studied by physicists who did not call it a perceptron. I forget what they called it. I think threshold unit is what they were called. I suspect that the electrical engineers also studied it because it's the obvious sort of switching kind of circuit. But it was also studied by early budding AI people, including someone called Seymour Papert, who wrote a book called Perceptrons. 60s or 70s, maybe early 70s. One of the things that were found about, well, let me start with asking you, what is the representational power of a single perceptron? It's kind of a funny question to ask because it's a different beast from a linear unit. A linear unit is a function from high-dimensional Euclidean space into a single number, right? A perceptron is a function from a high-dimensional Euclidean space into binary output, yes or no. So it's a different kind of function. It's not apples and oranges. But nonetheless, what kind of function is it?
It's the same, you have the same plane, but instead of saying how far you are from it, you say which side are you on.
Perfect, thank you. That's exactly the difference. Is you have the same plane, and you have the same richness of expression of expressing any linear plane, any hyperplane. But at the end, instead of saying how far you are from the plane and in which direction, you're just saying which side of the plane are you on. These kind of functions are called linear separators, or linear classifiers, or linear discriminators. They're all the same thing. They classify, they discriminate between two categories, and what's common to all of them is that the classification surface must be linear. So, for example, a single perceptron with the right weights could not discriminate. Okay. If you had these inputs, these are the positive examples and these are the negative examples, you could find a perceptron that would pass a straight line and separate them. But if they were not linearly separable, let's say you had a plus here, there would be no perceptron, no set of weights that you could choose that would properly classify all of these examples. So this is the essence of a linear classifier. So a single perceptron can classify all linearly separable data sets and cannot classify a single nonlinear separable one. So it's exactly, the representation power is exactly linear separability. This is as far as representation. Let's write it here. All linearly separable functions. As you vary the weights, you're changing the hyperplane and you're changing the linear separability surface. Alright, now let's deal with the question of learnability or search. You're given a training set data and you're asked to find the weights of a perceptron that would be consistent with it, namely classified correctly. So the training examples would look a little different than the training examples for the linear unit. The only difference would be in the output. Instead of the output being a continuous number, it would be a yes or a no. So you would have x11, x12, x1n, and then there would be a y here that would be either a 1 or a 0. Let's say 1. And then you have x21 through x2n, and maybe a 0, and 1, 1, 0, etc. And then xm1 through xmn, and here you would have ym, which is either a 0 or a 1. Same input, but the output is 1 or 0s. And now you're asked to find the weights of a single perceptron neuron that would classify it correctly. How do you do that?
Start off with a line and then go through each example and keep changing the angle or direction of the line until...
Okay, you start with some arbitrary hyperplane. You call it line because you're thinking 2 dimensions, but in general, you start with an arbitrary hyperplane, and that hyperplane will classify correctly some of the examples but not others. So, in our example here, you start with some line. The line also has a direction. There's a positive side and a negative side. Okay? The perceptron is capable of expressing for every line either this direction or the other direction. You can do it by inverting the sign of the weights. And let's say this is the positive sign, so I got this right, and this right, and this right, and this right, but these I got wrong. So now you're suggesting moving the line somehow to try to bring in more people, more data points to the right side without losing others. In 2 dimensions, as we have here, you have only 1 degree of freedom of how to change it, you know, clockwise, counterclockwise, certain distance. No, I guess you could also transition it, so you have 2 degrees of freedom. Of course, in the n-dimensional space, there are n different degrees of freedom of how to move that line. So I'm not arguing against it, I'm saying it's pretty hard to decide how to move it. But that would be a good heuristic to start with. Any other suggestions? Tom?
You could define a different error function, which counts the number of instances properly.
Okay, that's good. So this is following on the way we did it for the linear unit. Define an error function that's appropriate for this. What would be our error function? First of all, what is the error function a function of? Somebody else. Somebody who hasn't spoken here today. Weights, thank you. It's always a function of the weights. Error function of the weights is some kind of summation over your training examples. I use the same notation in the book and in the slides, so it will be D. D goes from 1 to M. Of the error of your current perceptron with regard to input number D. And the error of your current network is either it got it right or it got it wrong. Right? So how would we write that? We can use the delta function, the Kronecker delta, which gives you 1 if the two inputs are the same and 0 if they're wrong. Is that right, the mathematicians in the crowd? I think it gives you 1 when they're the same. So I would actually want to do 1 minus delta of the output of the network for input number D. I'm sorry, the desired output, the teacher output, and the actual output. This is just a fancy way of writing. If they agree, count it as 1. If they disagree, give 0. And then 1 minus that means that whenever they agree, you add 0 to the error count. And whenever they disagree, you add 1 to the error count. So this basically counts how many of the examples you got wrong. And if you want to normalize it, you can do 1 over n here, so that it's between 0 and 1. It will be the error rate. 1 over m, sorry. Some examples. So that would be one way of defining the error. And what do you do then, Tom? Okay, and then you do what you did with the linear units, which is gradient descent. You take the derivative. Okay? Can you do that? You have a hard time taking the derivative. Why?
Because the transfer function is not continuous.
The transfer function is not continuous and therefore not differentiable. So the problem hides here. Remember when you do the chain rule to take the derivative of the error, you have no problem pushing the partial derivative inside the square, inside the sum, and pushing it past this to here. But now you have the delta function, which is in itself non-differentiable. And what you have is here also a non-differentiable component. You have this. What does it correspond to intuitively? It corresponds to, if you're looking at gradient descent, you're considering making tiny changes in weight space. Tiny changes in weight space correspond to making tiny infinitesimal changes in the slope of this line. If the error function were differentiable, or at least if it were continuous in that line, that means that tiny infinitesimal changes in the line will make tiny infinitesimal changes in the error function, and you can see in which direction, and you can choose the direction that makes the biggest difference. But in our current situation where classification is hard, tiny changes, infinitesimal changes to the slope will not change your error function. It doesn't change how many you get right, how many you get wrong, unless you happen to touch one of these, and then an infinitesimal change would make a real finite non-infinitesimal change in the error. So that's not a good situation to be in. It's a situation, if you want to make it equivalent in the desert, is that you're always in the desert on a flat surface. But every now and then, boom, right? You go down or up. That's not it's not conducive to finding the lowest spot. So we can't do the gradient descent here.
What if you find a linear line that averages all the positive examples and a linear line that averages all the negative examples, and kind of average the two lines?
That would be a reasonable heuristic. That would be absolutely a nice heuristic to try. And it's certainly computationally easy. Once you define, you know who the positive examples are, and passing a hyperplane that is closest to all of them in some sense, so the center of gravity, is doable, I believe. But it's just a heuristic. Won't guarantee you anything.
Is an approximation to the Kronecker delta a continuous approximation to it?
Yes.
So
Yes.
that will allow you to do a gradient descent?
Yes. Can you bring that up a little bit later? Thank you. That's great. Okay, so we're in a situation where we have a single nonlinear unit. It's still not doing very exciting things. It only does linear separation. And we still don't have a way of learning it. We tried the gradient descent. What about the algebraic method that Dan suggested? What would it be here? The algebraic method here boiled down to a set of linear equations and mean squared error. The algebraic method with binary output, where you're trying to minimize the number of mistakes in the binary output, results in an algebraic problem that we don't know how to solve. In fact, we don't know how to solve in polynomial time. So there was a lot of work actually trying to solve that too. It's related to integer programming, which is a known hard problem. The problem comes from the fact that the output is discrete and therefore jumps as opposed to continuous. We now have reason to believe that this problem is intractable. I don't know what the current state of computation or computability or complexity theory is, if it's been proven that it's NP-complete or not, but it is generally accepted as an intractable problem. We don't know how to solve it. Seymour Papert didn't know that. He derived an algorithm for learning a single perceptron that was based on your idea here of making incremental changes. And he proved some interesting properties for it. Let me first show you the algorithm. It's called the perceptron learning algorithm. Or perceptron training algorithm. So the perceptron training algorithm, just like the gradient descent algorithm, starts with some random values of the weights and makes incremental changes. Unlike the gradient descent, there's no computation of gradient. But what there is something very similar. You start with some place in weight space, and you calculate which examples you do right by and which examples you don't. Which examples you get correct and which examples you don't. Those that you get correct, you ignore. Those that you get incorrect, you make small adjustments along each one of the weights proportional to the value of the input of these examples that you got wrong. So first, the high-level description of the algorithm, very similar to gradient descent. The new weight for the next iteration consists of the old weight plus the change in the weights. And the change in the weight along any one dimension this is the heart of the rule. This is proportional to, this is like the step size. This is whether you made an error or not. T minus O, T is the target or desired output, O is the actual output. T minus O, if you got that example right, is 0, and therefore it will not contribute. If you didn't get it right, it's either -1 or +1, depending on whether you got it wrong this way or that way. And Xi is how active is the current input number I, or dimension I, in the current training example that you're using. So the perceptron training algorithm was formulated as applying iteratively to one example at a time. But you could also apply it to all the examples together and sum them before you make the change. It was analyzed more in the incremental steps. So you take one example at a time, you go through it. If you got it right, then this would be 0 regardless of I. So there would be no changes in any of the WIs. If you got it wrong, this would be fixed at either +1 or -1, and then the change in each particular weight would be proportional to the value of the corresponding input, either positive or negative, large or small. And you keep going through all the examples. You must include the examples that you did okay on, because as your weights change, something you did okay on before, you might not do well on next time. So you keep them all in the loop. And you keep doing that until you got them all right. And then you stop. Anything wrong with this algorithm?
May not converge.
It may not converge. So Papert proved something very important, and that is that if there is a solution, you will find it. So if the problem is linearly separable, the perceptual learning algorithm will converge, and will converge to the right solution, to a solution. There may be more than one. Of course, you know that if there is no solution, there is no way it can converge by definition. If there's no solution, there will be for any set of the value of the weights, there would be at least one example that is misclassified, and therefore the algorithm did not converge. So it's one of those cases where when you stop, you know you got there, but until then, you don't know if you'll ever get there. After Papert came people who proved some other comforting properties, such as that even if there is no solution, the algorithm will converge, will do the best it can in a sense, that will tend to almost converge to an area where it makes minimal errors. So it would maybe oscillate between getting this one wrong and getting that one wrong. But the main problem is that we don't know. It doesn't tell us whether the problem is fundamentally linearly separable or not. And there are variations of this, of minimum error, but then it's not pure perceptron anymore. Did you have a comment?
I was going to ask, is it actually guaranteed to reach the global minimum error?
I don't think it's guaranteed, no. I don't know. In the special case where the global minimum is 0, it's guaranteed to reach it. What exactly it does when the global minimum is not 0, I don't know. Okay, so we have a learning result here, but it's not ideal. It always says if there is a solution, we'll find it. You could convert it into something pragmatic, like saying let it run for 2 hours, and if it didn't find it, I'll give up. I will not promise that there's no solution, but in many cases it will find it. And if not, it's likely to find something close to minimum. Just make a few errors. There are a few other theoretical problems with it. This thing, this eta, this step size, nobody tells you what it should be, and again you have the same problems with gradient descent. If it's too small, it'll take too long to converge. If it's too large, it may not hit the lowest possible error rate. In fact, I think there is a result that if the eta, the step size, is small enough, you will get to the lowest possible, I think. But nobody tells you what small enough is. Very similar to gradient descent in that regard. So we have a learnability result that's somewhat positive but not perfect. Yes?
I think since we were just telling the direction that the point line with respect to the plane, there will be so many solutions. There cannot be one.
Yes, there will be many solutions because the space of solutions is continuous. The space of error is discrete. So in this case, suppose you found a line that gives you the minimum error, you can wiggle it, minimally, have infinitesimally many solutions by wiggling it, sure. But in a way, they're all implementing the same. Well, they're not implementing the same thing. They implement the same thing with regard to the training examples, but they make some difference with regard to possible future examples. Okay. To depress you even further, remember that the representation power here is nothing to write home about. It's just linearly separable functions. So what do we do? What do we get if we put a lot of perceptrons together? So now we talk about a network of perceptrons. So number 3 was a single perceptron, and number 4 is going to be a network of perceptrons. The first thing to notice is that If you have a network of perceptrons, that means a single perceptron in the middle of the network receives input from other perceptrons. Because these other perceptrons produce as output only two values, say 0 and 1, then each perceptron in the middle of the network is functioning as a binary function, as a function of binary inputs. Whereas until now they all function as a function of continuous inputs. So the first layer of perceptrons operate on continuous space, but all the other subsequent layers operate on binary space, which is okay. The function overall is still a function from a continuous space to some binary output. So what is the representation power of a network of perceptrons? The same as a single perceptron. So you think it replicates the story we had with linear units. So specifically you cannot classify anything more than linear decision surface. Okay? Please?
All Boolean functions or Boolean functions?
All Boolean functions.
Like all and or XOR.
All and ors. Okay. Does everybody see why you can represent ands and ors? So if you think of a perceptron as, let's say, a function of two Boolean inputs, two binary inputs. This is input x1, this is input x2. You can implement an AND. Remember that x2 could be 0, 1, and x1 could be 0, 1. We can implement an AND by, for example, setting the weights here, W1 equal 1, W2 equal 1, and the threshold, what threshold will implement an AND? 1.5? 1.5, which is the same as having a W0 of negative 1.5. And that means that when both x1 and x2 produce a 1, the total sum weighted by the weights of 1 would be 1 times 1 plus 1 times 1, that's a 2, that's greater than 1.5, and therefore this is past its step function and it will produce a 1. Where either of these is a 0, the total weighted input coming in would be only 1, it's less than 1.5, and therefore the unit as a whole would produce a 0. So this implements an AND of x1 and x2. How would you implement an OR? By minimal change from here? Change the threshold from 1.5 to 0.5. You could do 1, 2, but then we have to worry about, did we do greater than or equal or just greater than? So instead of worrying about that, I'll just make it a 0.5. Can you do x1 and not x2? Change the weights. Which weight?
Make x1 heavier.
I'm sorry?
Make x1 heavier.
Make x1.
Make the weight of x1 heavier.
Make the weight of x1. I lost the last word.
Heavier, like 2 or 3, and then we change the trend.
Larger, 2 or 3. Say 3. I want to implement x1 and not x2. So you're saying heavier, larger weight here. What would the threshold be now? 2.5? 3.5. So when will this unit say yes? It will say yes when this is on and this is on. What are we missing here, please?
Make the weight of 2 negative.
Make the weight of 2 negative. Negative 1. And now what threshold should we choose? 2.5? Let's try 2.5. If this one is active, you get 3 units of juice coming up here. And then if this one is not active, you don't get anything here. So 3 units is more than 2.5. It says yes. But when Y2 is also active, you get -1 unit of juice. So you get 3 minus 1 gives you 2, which is not enough to pass the threshold. So that would work. As you can see, there are many different solutions. You can change the threshold a little bit. You can multiply all the weights by a constant. It would still be the same. But it is true that you can implement any binary function this way. Not only of 2 binary inputs, but of any n binary inputs. Not with a single neuron, but with a single neuron, you can implement a binary function of, I'm sorry, when I say any binary function, let me take that back. You can implement AND, you can implement OR, you can implement AND OR and NOT. Can you implement an XOR? X1, X2, with a single perceptron. Yes?
It's not linearly separable. So you need like chains of neurons.
The XOR problem for 2 binary variables is not linearly separable, and therefore you cannot do it with a perceptron. If you want a geometric representation, if this is x1 and this is x2, here are the 4 possible values. Right? x1 equals 0, y1 equals x2 equals 0, and then here they're both 1. And AND corresponds to passing a line here, singling out the case where they're both on. This is the AND line. And OR, where is the line for OR? It's right here. It's the same slope, but moved down. That corresponds algebraically to keeping the same weights, but changing the threshold. This is the OR line. I should mention for every line there's a direction. This is the positive direction, this is the negative direction. Positive direction, negative direction. And any hyperplane that can be implemented can also be implemented with the reverse polarity. You just need to invert the weights. Now to implement an XOR, we will need some hyperplane that makes this positive. I'm sorry, this is negative. It's this negative, and this negative, and this positive, and this positive. And there is no hyperplane that can do that. It's a non-linearly separable problem. And therefore, a single perceptron cannot do that. But, we were talking about networks of perceptrons. Using AND, OR, and NOT, in combinations, you can implement any Boolean function of n variables. So one thing that a network of perceptron can do is, if you treat the input as Boolean, if your inputs are all binary, you can compute any Boolean function of these n variables. I'd like you to think of ways of doing that, like generalized way of coming up with the weights for doing that. It's not hard. A separate question is, if your inputs are continuous, now you're in the space of mapping continuous space to binary output, 1 or more binary outputs. Can you implement any of those? And the answer is yes. Given enough intermediate units, given a large enough network and the topology of your choosing, you can approximate any continuous function of n variables. Keep in mind that perceptrons produces output only 2 values, 0, 1. So I'm talking about functions from a continuous space into the space of 1 and 0, but you can have more than one output. You can have a set of binary outputs, and therefore you can approximate any continuous output as well, because you can break down the output into, let's say, its decimal representation or its binary representation, and then use a separate unit for each one of the digits of the binary representation. So a network of perceptron is a universal approximator. It can approximate any function as long as you give it enough units to work with. Can you learn it? Given training data, can you learn a network of perceptrons? So think about it and read the chapter, please. Chapter 3, I think, or is it 4? Neural networks. And we will continue and hopefully finish in our next lecture.